Section: Introduction. We're diving into the world of visual representation learning, a key area of study in computer vision. This field has seen significant advancements since the advent of deep learning. Two main types of deep foundation models, convolution neural networks, CNNs, and vision transformers, ViTs, have been widely used in various visual tasks. Both have been successful in creating expressive visual representations, but ViTs often outperform CNNs. This is due to their global receptive fields and dynamic weights, made possible by the attention mechanism. However, the attention mechanism has a downside. It requires a lot of computational power, especially for tasks that require dense predictions, like object detection or semantic segmentation. To address this, researchers have tried to improve the efficiency of attention by limiting the size or stride of computing windows. But this comes at a cost. It restricts the scale of receptive fields. This challenge inspired us to create a new visual foundation model that maintains the benefits of global receptive fields and dynamic weights, but with linear complexity. We drew inspiration from the recently proposed state-space model and developed the visual state-space model, V Mamba, for efficient visual representation learning. The key to VMamba's success in reducing attention complexity comes from the selective scan space-state sequential model, S6, which was originally designed for natural language processing, NLP, tasks. Unlike the traditional attention computation approach, S6 allows each element in a 1D array, like a text sequence, to interact with any of the previously scanned samples through a compressed hidden state. This effectively reduces the quadratic complexity to linear. However, applying this strategy directly to a patchified and flattened image can result in restricted receptive fields, as the relationships against unscanned patches cannot be estimated. We call this the direction-sensitive problem and propose to solve it with the newly introduced cross-scan module, CSM. Instead of scanning the spatial domain of image feature maps in one direction, either column-wise or row-wise, CSM uses a four-way scanning strategy. It scans from the four corners of the feature map to the opposite location. This ensures that each element in a feature map integrates information from all other locations in different directions, providing a global receptive field without increasing the linear computational complexity. We conducted extensive experiments on various visual tasks to test the effectiveness of V Mamba. The results showed that V Mamba models perform as well as or better than benchmark vision models like ResNet, ViT, and SWIN on ImageNet 1K. We also tested V Mamba on downstream dense prediction tasks. For example, V Mamba Tiny, Small, Base, with 22, 44 75 million parameters respectively, achieved 46.5%, 48.2%, 48.5% map on COCO using the mask RCNN detector and 47.3%, 49.5%, 50.0% MIOU on ADE20K using UperNet with 512 by 512 inputs. This shows that V Mamba has the potential to be a powerful foundation model. Interestingly, when larger images are used as input, the flops of ViT increase significantly faster than those of CNN models, despite usually still exhibiting superior performance. However, V Mamba, which is essentially a foundation model based on the transformer architecture, is able to attain performance comparable to ViT with a steady increase in flops. In summary, we propose V Mamba, a visual state space model with global receptive fields and dynamic weights for visual representation learning. V Mamba presents a new option for vision foundation models, extending beyond the existing choices of CNNs and ViTs. The cross-scan module, CSM, bridges the gap between 1D array scanning and 2D plane traversing, facilitating the extension of S6 to visual data without compromising the field of reception. V Mamba achieves promising results across various visual tasks including image classification, object detection, and semantic segmentation, underscoring its potential to serve as a robust vision foundation model. Deep neural networks have significantly advanced research in machine visual perception. There are primarily two prevalent types of visual foundation models, CNNs and ViTs. Recently, the success of state space models, SSMs, has illustrated their efficacy in efficient long-sequence modeling, attracting attention in both the NLP and CV communities. Our study follows this line of work and proposes V Mamba, a SSM-based architecture for data modeling in the vision domain. V Mamba contributes as an alternative foundation model to the community, alongside CNNs and ViTs. CNNs are landmark models in the history of visual perception. Early CNN-based models were designed for basic tasks, like recognizing handwritten digits and classifying character categories. The distinctive characteristics of CNNs are encapsulated in the convolution kernels, which use receptive fields to capture visual information of interest from images. With the aid of powerful computing devices and large-scale datasets, increasingly deeper and efficient models have been proposed to enhance performance across a spectrum of visual tasks. ViTs, adapted from the NLP community, have shown to be a potent perception model for visual tasks and have quickly evolved into one of the most promising visual foundation models. Early ViT-based models usually require large-scale datasets and appear in a plain configuration. Later, DET employs training techniques to address challenges encountered in the optimization process, and subsequent studies tend to incorporate inductive bias of visual perception into network design. SSMs are recently proposed models that are introduced into deep learning as state-space transforming. Inspired by continuous state-space models in control systems, combined with hippo initialization, LSSL showcases the potential in handling long-range dependency problems. However, due to the prohibitive computation and memory requirements induced by the state representation, LSSL is infeasible to use in practice. To solve this problem, S4 proposes to normalize the parameter into diagonal structure. These models are then integrated into large representation models. Those models mainly focus on how state space models are applied on long-range and casual data like language and speech, such as language understanding, content-based reasoning, pixel-level 1D image classification. Few of them pay attention to visual recognition. The most similar work to ours is S4ND. S4ND is the first work applying state-space mechanism into visual tasks and showing the potential that its performance may compete with ViT. However, S4ND expands the S4 model in a simple manner, fails on efficiently capturing image information in an input-dependent manner. We demonstrate that with the selective scan mechanism introduced by Mamba, the proposed V Mamba is able to match existing popular vision foundation models like ResNet, ViT, SWIN, and ConvNext, showcasing the potential of V Mamba to be a powerful foundation model. Section Summary. In this section, the authors introduce a novel visual foundation model called V Mamba for efficient visual representation learning. V Mamba utilizes a visual state space model, VSSM, inspired by the selective scan space state sequential model, S6, to reduce attention complexity from quadratic to linear. To address the direction-sensitive problem in visual data, a cross-scan module, CSM, is introduced, enabling global receptive fields without increasing computational complexity. Extensive experiments demonstrate the effectiveness of V Mamba across various visual tasks, making it a promising alternative to CNNs and ViTs as a robust vision foundation model. Section Method. In this section, we'll delve into the key concepts related to V Mamba, including state space models, the process of discretization, and the selective scan mechanism. We'll also provide a detailed explanation of the 2D state space model, which is a fundamental component of V Mamba. Lastly, we'll discuss the overall architecture of V Mamba. State space models, often abbreviated as SSMs, are typically seen as systems that remain constant over time and map an input to an output. These models are usually expressed as linear ordinary differential equations, with parameters that include a state size and a skip connection. SSMs, being continuous time models, can be challenging to integrate into deep learning algorithms. To overcome this, we use a process called discretization. The main goal of discretization is to convert the continuous ordinary differential equation into a discrete function. This conversion is important because it aligns the model with the sample rate of the signal in the input data, making computations more efficient. Unlike most models that focus on linear time-invariant SSMs, V Mamba stands out by incorporating the selective scan mechanism, also known as S6. In S6, the matrices are derived from the input data. This means that S6 is aware of the context within the input, ensuring dynamic weights within the mechanism. However, S6 processes the input data in a causal manner, meaning it can only capture information within the scanned part of the data. This works well for tasks involving temporal data, but it can be challenging when dealing with non-causal data like images or graphs. To solve this, we propose scanning data in two different directions, forward and backward, without increasing computational complexity. Images, despite their non-causal nature, contain 2D spatial information. To address this, we propose the cross-scan module, CSM. In CSM, we unfold image patches into sequences and scan them in 4 different directions. Each sequence is then reshaped into a single image, and all sequences are merged to form a new one. The integration of S6 with CSM, referred to as the S6 block, serves as the core element to construct the visual state space, VSSS, block, which is the fundamental building block of V Mamba. Now, let's discuss the overall architecture of V Mamba. V Mamba starts by dividing the input image into patches using a stem module, similar to vision transformers, but without flattening the patches into a 1D sequence. This preserves the 2D structure of images. V Mamba then stacks several VSS blocks on the feature map, maintaining the same dimension. Hierarchical representations in V Mamba are built by down-sampling the feature map through a patch merge operation. This procedure is repeated to create different stages with varying resolutions. All these stages collectively construct hierarchical representations similar to popular CNN models and some vision transformers. The resulting architecture can serve as a versatile replacement for other vision models in practical applications. We develop V Mamba in 3 distinct scales: V Mamba Tiny, V Mamba Small, and V Mamba Base. The computational complexity for all models is assessed using a standard input size. We plan to introduce additional architectures, such as a large-scale model, in future updates. Section Summary. In this section, the authors introduce the preliminary concepts of V Mamba, including state space models, the discretization process, and the selective scan mechanism. They also present the 2D selective scan approach, which allows for scanning data in both forward and backward directions to capture spatial information in images. The overall architecture of V Mamba is described, which involves partitioning the input image into patches and stacking visual state space, VSS, blocks to create hierarchical representations. Section: VSS block. Let's talk about the VSS block. Picture it like this. We have an input that first goes through a linear embedding layer. Then, it splits into 2 separate information streams. One stream goes through a depthwise convolution layer with a 3x3 filter, then it's activated by a CLU function before entering the core SS2D module. The output from the SS2D module is normalized and then combined with the output from the second information stream, which has also been activated by a CLU function. This combination gives us the final output of the VSS block. Unlike vision transformers, we don't use position embedding bias in our model, V Mamba, because of its causal nature. Our design is different from the typical vision transformer structure, which usually follows a sequence of operations: normalization, attention, normalization, and MLP in a block, and discards the MLP operation. As a result, our VSS block is less complex than the ViT block, allowing us to stack more blocks while keeping the total model depth within a similar budget. Now, let's talk about our experiments. We tested V Mamba against popular models like CNNs and vision transformers across various tasks, including image classification on ImageNet-1K, object detection on COCO, and semantic segmentation on ADE20K. We also conducted analysis experiments to better understand VMamba's architecture. For image classification on ImageNet-1K, we trained VMamba from scratch for 300 epochs, with the first 20 epochs for warm-up, using a batch size of 1024. We used the AtomW optimizer with betas set to 0.9 and 0.999, a momentum of 0.9, a cosine decay learning rate scheduler, an initial learning rate of 0.001, and a weight decay of 0.05. We also used label smoothing and exponential moving average techniques. Our results showed that VMamba outperformed popular CNN models and vision transformers. For example, VMamba-T achieved a performance of 82.2%, surpassing REGNETY4G by 2.2%, DETS by 2.4%, and SWIN-T by 0.9%. These results highlight VMamba's potential as a robust foundational model. For object detection on COCO, we used the MSC-OCO 2017 dataset and trained our model using the detection library. We fine-tuned the pre-trained classification models for both 12 and 36 epochs. The learning rate was initially set to 0.0001 and was reduced by a factor of 10 at the 9th and 11th epochs. We used multi-scale training and random flip with a batch size of 16. Our results showed that VMamba consistently outperformed other models in box, mask average precision on COCO, regardless of the training schedule. For instance, with a 12-epoch fine-tuning schedule, VMamba models achieved object detection maps of 46.5%, 48.2%, and 48.5%, surpassing SWIN models by 3.8%, 3.6%, and 1.6% map, respectively. These results underscore the potential of VMamba in downstream dense prediction tasks. Section Summary. The VSSS block in VMamba consists of an initial linear embedding layer, followed by two information flows. One flow goes through a depthwise convolution layer and the SS2D module, while the other flow undergoes a CLU activation. The outputs of these flows are combined to produce the final output. In experiments, VMamba achieves superior performance in image classification on ImageNet-1K, surpassing popular CNN models and vision transformers. It also outperforms other models in object detection on COCO, demonstrating its potential in downstream dense prediction tasks. Section. Semantic segmentation on ADE20K. We've been working on semantic segmentation using the ADE20K dataset, building on the SWIN model by adding an OOPR head to the pre-trained model. We used the AtomW optimizer and set the learning rate to 0.00006. The fine-tuning process took 160,000 iterations with a batch size of 16. We used an input resolution of 512 by 512 pixels, but also tested with 640 by 640 pixels and multiscale testing. Our results, which are detailed in the table, show that our model, VMamba, outperforms other models in terms of accuracy. The VMamba-T model achieved a mean intersection over union, MIOU, of 47.3% with a resolution of 512 by 512 pixels and 48.3% MIOU with multiscale input. These scores are higher than those of all other models we compared it with, including ResNet, DET, SWIN, and Convenext. Even the smaller VMamba SB models performed well with 640 by 640 pixel inputs. We also conducted experiments to assess the effective receptive fields, ERFs, of various models. The ERF measures how much the input of a model affects its output. We visualized the ERF of the central pixel with an input size of 1024 by 1024 pixels and compared VMamba with four other models, ResNet 50, Convenext T, SWIN T, and DETS, ViT, both before and after training. Our observations showed that only DET, ViT, and VMamba had global ERFs, while the other models had local ERFs. However, DET, ViT, has a high complexity cost. Unlike DET, ViT, which activates all pixels evenly, V Mamba activates all pixels but emphasizes cross-shaped activations. This is due to the cross-scan module scanning mechanism, which prioritizes long dependency context over local information for each pixel. Interestingly, V Mamba initially had only a local ERF before training, but after training, it became global. This suggests that the model adapts to enhance its image perception capabilities. This is different from DET, which had nearly identical ERFs before and after training. We also conducted experiments on input scaling, measuring top 1 accuracy on ImageNet -1K and flops. V Mamba showed the most stable performance across different input image sizes. As the input size increased from 224 by 224 pixels to 384 by 384 pixels, only V Mamba showed improved performance, with V Mamba S achieving 84% accuracy. When we evaluated flops using different image resolutions, the V Mamba series showed a linear growth in complexity, similar to CNN models. V Mamba's complexity is consistent with carefully designed vision transformers like SWIN. However, only V Mamba achieved a global effective receptive field, ERF. DET, which also has a global ERF capability, showed a quadratic growth in complexity.